Hello friends, we will start with the new lecture, lecture 5, and that is going to cover two effects on the flow stress which we did not talk about in the previous lecture, that is the effect of strain rate and temperature. Okay. So, let me define strain rate to you first. Okay. So, basically we will be talking in this lecture, so flow stress as a function of strain rate and temperature. These two effects we did not discuss earlier. So, now a new term has come here, strain rate. So, strain already we know what do we mean by strain. Okay. So, strain rate is basically, you can say d epsilon divided by dt, that is the what is at what rate I am putting the strain. So, that is a very important parameter during the deformation process. Okay. So, in rolling, forging, extrusion, all these processes, if you see whether I am deforming slowly, okay, or I am deforming at a very high rate, okay, some idea about this rate you must be having from the your basic courses, that impact is one of the type of loading condition, and one is where you do very slow deformation. So, a very slow deformation and a very high deformation where you call it as impact. Okay. So, the material behavior is very different in these two cases. So, a ductile material which is showing a good amount of ductility in case of a slow strain rate test becomes a almost like a brittle material in a impact kind of condition. Okay. And impact kind of conditions are very important in case of automobile application nowadays, where they want to know the crash worthiness, okay, that how much energy a material will take during a high speed collision. Okay. So, strain rate is a very important parameter in deformation, industrial deformation also, that at what rate I am deforming the material. Okay. So, if I want to show the effect of strain rate, okay, now we will also bring the effect of temperature here. So, the earlier flow curve which I showed you in the previous lecture, okay, you can consider that all those type of stresses, flow stress curve you will see at in a material at a temperature which is less than 0.4 of Tm. So, what is Tm? Tm is the melting point of material. Okay. So, for example, melting point of material is, and of course, you have to take it in Kelvin. Okay. So, a melting point of material is suppose 1000 Kelvin. Okay. Then, if you are deforming the material at lower than 400 Kelvin, okay, then you will see the flow stress curve which I showed you in the previous lecture. But if I am deforming at a temperature which is more than 0.4 of its melting point, so let us say more than 400 Kelvin, okay, then you will see now the effect of temperature also on the flow stress curve. Okay. So, first to define the effect of strain rate on flow stress, okay, again we can take the let us now, because we will be always talking about true stress from this lecture, let us I will remove this T part here. So, if I am writing sigma simply, it is true stress, and epsilon is of course true strain. Okay. And let us say I am taking a simple deformation condition which is basically a steady state condition. So, after the yielding you have a steady state flow. Okay. So, usually you will see curves like this, another one like this. Okay. So, I have drawn different curves. Okay. Now, the temperature is constant here. So, these are all at constant temperature, some temperature which is more than 0.4 Tm. Okay. So, let us say this constant temperature is more than 0.4 Tm. Okay. And so, now what is the difference between all these flow stress curve, that they are at different strain rate. Okay. Okay, they are all at different strain rate. Okay. And from their flow stress values I can say that epsilon dot 4 is more than epsilon dot 3, more than epsilon dot 2, more than 1. Okay. So, lower the strain rate, the flow stress will be low. Okay. Higher the strain rate, the flow stress will be high. Okay. So, if I want to give a relationship to this kind of effect of strain rate on the stress, okay, a very generalized relationship between stress and strain rate will be something like this. So, this is C1, okay, epsilon dot to the power m at constant strain and temperature. So, already we have said that all the plots are at constant temperature, and constant strain means suppose I just take a particular strain value here, okay, and find out that for epsilon 1 dot what was the stress sigma 1, sigma 2, sigma 3, sigma 4 and so on. Okay. So, they will follow a relationship like this, where m is strain rate, you can call it as hardening also, or sometime we call it as sensitivity index, that what is the sensitivity of stress to strain rate. Okay. So, this m is defining that strain rate sensitivity index of the stress, okay, or you can also call it as strain rate hardening. So, it is similar to what we saw in the previous lecture where we talked about strain hardening. So, at low temperature material experiences strain hardening. You can see in these curves the strain hardening part is very small, okay, and in fact, after a certain strain there is no effect of strain on the stress. So, there is no strain hardening at all. Okay. So, at higher temperature deformation the strain hardening is of the material is very low. Okay. So, the strain rate hardening is a very important parameter which stabilizes the deformation or which gives a uniform deformation. Okay. So, material experiences strain rate hardening, and how to find out this strain rate sensitivity index, again we can do similar thing what we did earlier. If I take logarithmic on both the side, it will become something like this. C1 is your some material parameter, okay, and m ln epsilon dot. Okay. So, basically if I plot ln of epsilon dot versus ln of sigma, the slope should give me the strain rate sensitivity index. So, okay. So, if I plot ln of sigma versus ln of epsilon dot, I should get some point like this. Okay. If I fit a linear curve here, the slope should give me the strain rate sensitivity of the material. Okay. And strain rate sensitivity is usually in hot deformation cases, you will find for industrial hot deformation processes like rolling, extrusion and all that, the value may be somewhere between 0.1 to 0.2, okay, for hot deformation in industry. Okay. Another way important deformation phenomena in materials what we call as superplasticity. I am not going to detail right now, just to give you a idea. Okay. The value will be more than 0.4, okay, and so it is highly strain rate sensitive condition. Okay. And just to kind of connect it with your other understanding, for example, fluid mechanics or fluid, okay, the Newtonian viscous fluids have m equal to 1. So, for Newtonian viscous fluid the strain rate sensitivity index is 1. Okay. So, for other materials either it can be less than 1, in this case it is less than 1, okay, in materials, okay, and usually it is in the range of or lower than normal hot deformation 0.1 to 0.2, superplasticity more than 0.4, okay, a very important parameter to have during the hard deformation process. Now, how to find out that what is the strain rate which you are imposing in the during a tensile test, okay, which we normally do in the labs. Okay. So, just to give you an idea that if I want to find out that what is the strain rate at which I am deforming the material, basically when you deform the material, what you control or what your machine controls is the cross head speed, that how fast or slow it is moving the cross head. It is not going to give you a strain or strain rate, okay. That you have to or of course, there are softwares which can do that, but just to have an understanding of that I am giving you an idea here. So, basically cross head velocity, if you see cross head velocity, if I want to find out, okay, V will be equal to dl upon dt. Okay. So, what is the change movement of the cross head divided by the time it takes in that movement. Okay. So, if I in terms of simple engineering strain or in strain rate, if I want to find out, then it will be E dot will be equal to dE upon dt, that will be equal to d L minus L naught divided by L naught upon dt. This is all in differential. Since L naught is your constant, so it comes out 1 upon L naught, and this become d L by dt. Okay. So, my E dot becomes B upon L naught. Okay. So, if I know my cross head speed, that okay, I am moving cross head at this speed, which I can easily find out from my machine, and if I know my original length, I can easily get the engineering strain rate. Okay. So, engineering strain rate is the rate which or it is the original strain rate which you are imposing. Okay. You will be taking only the original cross sectional original length of the sample. But again, as we said that during deformation your continuously length is changing. Okay. So, whether you are imposing a initial strain rate, initial constant strain rate, or you are imposing a true strain rate. Okay. That is also again a kind of a debate you can have, okay, that whether I should impose a constant strain rate or I should impose a continuous or constant strain rate. So, this is my initial strain rate, and another can be my true strain rate. Okay. For that, epsilon dot will be equal to d epsilon by dt, that will be equal to d ln of L upon L naught by dt, that will be equal to 1 upon L dl by dt, that is equal to V by L. So, continuously the length is now changing. Here it was a constant length, it is a instantaneous length. Okay. So, if I want to find out in terms of or if I have so now to have this kind of constant true strain rate, okay, your machine has to have a closed loop servo hydraulic machine. That means it is continuously feeding that what is the change in the length, okay, or change in the extension to the machine, and you can see that to maintain the cross head speed constant to maintain the true strain rate constant, and since my length is continuously changing, my velocity also has to continuously change. Whereas, in this case my velocity will remain constant to maintain, because my L naught is constant. So, I will have a constant engineering strain rate. Okay. But here it has to continuously change the velocity as the deformation progresses. So, you have to have a closed loop type of machine which is continuously feeding the that what is the now the latest length, okay, and accordingly the velocity has to change. Okay. So, now you can see there is, since the length is increasing, okay, so velocity has to continuously decrease. Okay. So, this actually nowadays all these are done by software. So, if you want a constant true strain rate, you can give that kind of condition and it will be the program will be following that using a loop. Okay. Now, what will be the effect of temperature? So, again I am drawing some flow stresses here, sigma versus epsilon. Okay. So, again I am taking a simplified steady state type of flow, okay, and giving them some temperature T1, T2, T3, and these are all done at constant strain rate. Okay. So, when you want to change temperature, you have to fix the strain rate as constant and keep changing the temperature for different samples, or you can do at a constant temperature and keep changing the strain rate for different samples. Okay. And from the flow stress value, I can tell you that my T1 will be more than T2, it will be more than T3. So, it is exactly opposite of what we saw in case of strain rate. In the strain rate, I said T3 is epsilon dot 3 will be more than epsilon dot 2 than epsilon dot 1. That was the case in case of, but here for increase in flow stress the condition will be like this. Okay. And again we can define this behavior using some relationship between stress and temperature, and that will be something like this: sigma C2 exponential Q by RT at constant strain and strain rate. Okay. So, again I can take at a particular strain rate strain here at different temperature, what is the at T1 sigma 1 is the flow stress, T2 sigma 2 is the flow stress, T3 sigma 3 is the flow stress, and so on. Okay. So, you can see that it is in the denominator. So, as temperature is going to increase, my stress is going to decrease. This Q is the activation energy for deformation, okay, and its value is joule per mole. Temperature is of course in Kelvin, okay, the temperature is in Kelvin, and R is your universal gas constant. Okay. C2 is again some constant for material. Okay. So, again I can find out what will be the value of Q here. Okay. If I again take logarithmic on both the side, it will become something like this: C2 plus Q by RT. Okay. So, if I plot a curve between ln of sigma versus 1 by T, okay, then I will be getting so 1 by T is increasing here, means temperature is decreasing here. So, you can see my flow stress has to increase here, okay, different values coming from here. I can plot a straight line here, fit a best fit line, and the slope will give me the value of Q by R. So, from here I can find out that what is the activation energy for deformation. So, as we saw that when we were relating stress with the strain rate, important parameter is the strain rate sensitivity index. What is the sensitivity of the stress to strain rate? When we are relating stress with the temperature, the important parameter which relates temperature with the stress is the activation energy, that what is the activation energy of deformation. Okay. Now, we can try to see some more type of curves. I have shown you a very simple curve till now. Okay. Now, you can see that there are variety of curves which flow curves which you can find out when you are doing a deformation at high temperature. Okay. So, that I will show you. So, this different type of flow curves. So, one we have already seen, okay, at low temperature sigma versus epsilon. You will have some elastic part, then plastic part and then deformation and some fracture here. Okay. So, you can see that in this case the flow stress is continuously increasing as a function of strain. Okay. So, this is what you will get usually at temperature lower than 0.4 TM. Okay. This kind of behavior you will always see, where you will only get phenomena what we call as work hardening. Okay. As you increase the temperature now, okay, another type of curve again we have seen just now, okay, that you have elastic part, then this, and then steady state behavior. So, this is what we call as a steady state behavior, because there is no change in the stress value as a function of strain. So, everything is in steady state condition, there are no changes in the material. Okay. And this happens when how we get work hardening, because of multiplication of dislocation, your dislocation density keep increasing. Okay. So, since we are not getting anything here, that means the dislocation multiplication or dislocation generation is kind of nullified by some other mechanism. So, what is that mechanism? Because we are deforming at a temperature more than 0.4 TM here. Okay. Now, other microstructural processes will start, and one of them is called dislocation recovery, and the dislocation recovery is helped by the vacancy concentration in the material. So, you must be knowing that equilibrium vacancy concentration of material increase exponentially with temperature. Okay. So, you may increase temperature linearly, but the vacancy concentration will increase exponentially, and these vacancies help the dislocation in recovery process. Okay. The actual mechanism is dislocation climb. Okay. So, dislocation recovery takes place. So, the number of dislocation which are generating, okay, the same number of dislocations are getting recovered. So, you because of that you get a steady state deformation. Okay. Now, another type of curve which you will see, I have not shown you till now, which will be something like this. So, it goes like this, make a hump, come down and become steady state. Okay. So, this is another type of curve, and a different microstructural process will take place here. This is, as I told you, recovery will be there. This is the type of curve which you will have when you are having dynamic recrystallization. All these terms we will see later on. Okay. Another type of curve which you can see instead of this is like this, it goes like this, goes up and something does something like this. Okay. So, instead of one hump you get multiple humps. Okay. Again, this is a process where recrystallization is happening, or dynamic recrystallization is happening. Okay, in multiple stage. Okay. And usually it happens at lower stress and higher temperature. So, when stress is lower and temperature is higher. So, again if you compare with this one, this will be at lower stress, higher temperature. Now, one interesting thing you can do is, if you see earlier also I was showing that the effect of strain rate and temperature is entirely different on the stress. Okay. If you remember, if I increase the strain rate, okay, or decrease the temperature, okay, my stress will increase. Okay. And if I do other way around, so there is a almost opposite effect of strain rate and temperature on stress, and we have given you two different equations for that. Okay. You can in fact a smart thing was done, okay, and done by two scientists, and on their name the parameter is known, and this parameter is called Zener-Holloman parameter, which we call it as Z. Okay. This combines both this effect in one. So, Z can be written as epsilon dot exponential q by RT. So, you can see epsilon dot and T both are now considered here, and sigma can be then just can be shown as some function of z, where both the effects are combined together and brought in a single equation. So, when your temperature is low, strain rate is high, means the z will be more and the stress will be more. When the strain rate is low, temperature is more, your z will be less, so your stress will be less. So, now sigma is a direct function of and for function we will see what kind of functions can be there, but it can be some function of the Zener-Holloman parameter. Okay. So, I think with this I have explained you different type of flow stresses which you will see in hot deformation, and what is the effect of two very important parameters which you control during deformation, okay, which is strain rate and temperature. So, how fast you are deforming and what temperature you are deforming. So, flow stress will be dependent on that, okay, and flow stress will also be keep changing depending upon what is the condition of deformation. So, whether you are deforming at what temperature, okay, or what strain rate, okay. So, different conditions will give you different type of flow stresses, and of course, there will be change in the microstructure accordingly, okay, and that is what we want when we are doing any hot deformation process. We want to change the microstructure, and those microstructure will help us giving in the properties which we want, okay. So, thank you.